Welcome to today's session. In this video, we'll explore problem number 1051, height checker. We'll break down the problem, analyze different approaches, and focus on how to solve it effectively. Let's dive in and start learning. In this problem, we are given an array called heights, which represents the heights of a group of students standing in a line. The goal is to figure out how many students are not standing in their correct positions if we were to arrange them in non-decreasing order of their heights. Essentially, we compare the students' current positions with their positions in a sorted version of the array. If the heights at a given position do not match between the original and the sorted arrays, that position is considered incorrect. For the input format, the heights array is a list of integers with a length ranging from 1 to 100. Each height is guaranteed to be between 1 and 100. The output will be a single integer that tells us the number of incorrect positions, and it will be of type int. Now, let's look at an example to better understand the problem. Suppose the input array is heights equals 1, 1, 4, 2, 1, 3. The sorted version of this array would be 1, 1, 1, 2, 3, 4. To find the number of incorrect positions, we compare each index in the original array with the corresponding index in the sorted array. At index 0, the value 1 matches 1, so this position is correct. At index 1, the value 1 also matches 1, so it's correct. At index 2, the value 4 does not match 1, which makes it incorrect. Similarly, at index 3, the value 2 matches 2, so it's correct again. At index 4, the value 1 does not match 3, so it's incorrect. Finally, at index 5, the value 3 does not match 4, marking it as incorrect as well. Adding up the incorrect positions for this example, we find 3 mismatches in total. So, the output for this input is 3. Let's consider another example. If the input array is heights equals 5, 1, 2, 3, 4, the sorted version of this array would be 1, 2, 3, 4, 5. Comparing these two arrays, we see that at index 0, the value 5 does not match 1, so this position is incorrect. At index 1, the value 1 does not match 2, which is also incorrect. At index 2, the value 2 does not match 3, making it incorrect. Similarly, at index 3, the value 3 does not match 4, and at index 4, the value 4 does not match 5. Every position in this case is incorrect. Since all 5 positions in this example are incorrect, the output is 5. To explore one more scenario, let's consider the input heights equals 1, 2, 3, 4, 5. In this case, the sorted version of the array is identical to the original array 1, 2, 3, 4, 5. When we compare the two arrays, every position matches. That means there are 0 incorrect positions, and the output is 0. This example illustrates a case where the input is already sorted, so no changes are needed, and no students are out of position. Finally, let's discuss the constraints and some edge cases to keep in mind. First, the number of students, n, is between 1 and 100, and each student's height is between 1 and 100. For edge cases, if there is only one student, the output will always be 0 because there is no one else to compare positions with. If all heights in the array are identical, no student will be out of position, and the output will also be 0. Similarly, if the array is already sorted, the output will be 0, as seen in the third example. On the other hand, if the array is sorted in strictly decreasing order, every position will be incorrect, and the output will equal n. For instance, if heights equals 5, 4, 3, 2, 1, all n positions are mismatched, resulting in an output of 5. To solve the height checker problem, we first considered the brute force approach. The intuition here lies in directly comparing the given heights array with a sorted version of itself. By sorting the array, we reveal the correct order of students by height, and mismatches can be identified by comparing the original array to this sorted version. This process involves creating a sorted copy of the heights array, iterating through both arrays simultaneously, and counting the positions where the two arrays differ. However, while conceptually simple, the brute force approach requires sorting, which has a time complexity of n log n. Additionally, storing the sorted array results in a space complexity of n. These factors make it less efficient than the optimized approach we will explore next. The optimized approach uses counting sort, which is ideal for this problem due to the small range of possible height values, specifically between 1 and 100. By leveraging counting sort, we can achieve better performance both in terms of time and space efficiency. The counting sort approach is more efficient because it avoids the overhead of general-purpose sorting. First, we initialize a frequency array, count, of size 101 to cover all potential heights from 1 to 100. As we iterate through the original heights array, we populate this frequency array by incrementing the index that corresponds to each height value. Once this is done, we use the frequency array to reconstruct the sorted order of heights by iterating through it and expanding each height based on its frequency. We then compare this reconstructed order with the original heights array to count mismatches. This method has a time complexity of O(n) for counting the heights, O(n) for reconstructing the sorted order, and O(n) for comparing the arrays, giving an overall time complexity of O(n). Importantly, the space complexity is O(1), because the frequency array has a fixed size of 101, regardless of the input size. The key insight here is that we don't need to fully sort the array in the traditional sense, we only need to identify mismatches relative to the correct order, which makes counting sort an optimal choice. When comparing the two approaches, we see clear trade-offs. The brute force approach, while straightforward and easy to implement, involves the unnecessary overhead of sorting the array, leading to a time complexity of O(n) log n. In contrast, the counting sort approach is both faster and more space efficient for this specific problem due to its linear time complexity and fixed size frequency array. However, it is specialized and relies on knowing the bounded range of input values, meaning it may not generalize well to other problems where the data range is unbounded. Ultimately, for this problem, counting sort is the optimal choice as it takes full advantage of the small and fixed range of height values, allowing us to solve the problem efficiently without unnecessary computational overhead. While the brute force approach provides a solid baseline, counting sort is clearly the better option for this scenario. To solve the height checker problem, we start by understanding the input and the goal. We are given an array called heights, where each element represents the height of a student standing in a line. The objective is to determine how many students are not standing in the positions they would be in if the array were sorted in non-decreasing order. The first step in the algorithm is to create a sorted version of the heights array, which we'll call sorted_heights. Sorting the array helps us identify the correct order of the students based on their heights. Next, we compare the original heights array with the sorted_heights array. During this comparison, we'll initialize a counter, mismatched_count, to 0. For each index in the array, if the value in heights is different from the value in sorted_heights, it means the student at that position is out of place. In such cases, we increment our counter by 1. This process ensures we identify every mismatch between the current arrangement and the ideal sorted order. Once the comparison is complete, the value stored in mismatched_count will represent the number of students who are out of their correct positions. This value is then returned or printed as the result. Now, let's focus on some key insights that make this approach effective. First, sorting the array provides the ideal arrangement of the students, which serves as a reference for comparison. By directly comparing the original array to the sorted version, we eliminate the need for additional operations like swapping or reordering. This keeps the implementation straightforward. In terms of efficiency, sorting the array requires O(n) log n time, and comparing the arrays runs in O(n) time. Overall, the algorithm operates with a time complexity of O(n) log n. Additionally, the approach naturally handles edge cases. For example, if the array is already sorted, the mismatch count will be 0. Similarly, if all elements are identical, the count will also be 0. Even in the case of a completely reversed array, the algorithm correctly identifies the total number of mismatches, which would equal the size of the array. To implement this algorithm, we utilize 3 key data structures. First, the input array height stores the original arrangement of student heights. Next, we create a new array, sorted_heights, to store the heights in sorted order. This allows us to directly compare the input with the ideal order. Finally, we use a counter variable called mismatched_count to keep track of how many students are out of place. The algorithm relies on 2 main operations. The first is sorting, which determines the correct order of students. Sorting is efficient, with a complexity of O(n) log n, making it suitable for the input size constraints. The second operation is a comparison, where we iterate through both arrays simultaneously to identify mismatches. This comparison step is linear, with a complexity of O(n), as we only make a single pass through the arrays. Notably, the algorithm handles edge cases naturally. For example, when the input array is already sorted or contains identical elements, no mismatches are found, requiring no additional code to address these scenarios. Now, let's analyze the algorithm's complexity in more detail. The time complexity is dominated by the sorting step, which takes O(n) log n. The subsequent comparison step adds O(n), resulting in an overall time complexity of O(n) log n. For space complexity, the algorithm requires O(n) additional space to store the sorted heights array. Therefore, the space complexity is O(n). To better understand how the algorithm works, let's walk through an example. Suppose the input array is heights equals 5, 1, 2, 3, 4. The goal is to determine how many students are out of place when compared to the sorted order. First, we sort the input array. The sorted version is sorted_heights equals 1, 2, 3, 4, 5. Next, we compare the two arrays index by index. At index 0, the original value is 5, but the sorted value is 1, so we increment the mismatch count. At index 1, the original value is 1, but the sorted value is 2, so we increment the count again. This process continues for all indices, with mismatches at every position. By the end of the comparison, we have a total mismatch count of 5. Therefore, the algorithm returns mismatched_count equals 5. For an edge case, consider an already sorted array, such as heights equals 1, 2, 3, 4, 5. In this case, the sorted_heights array is identical to the input, and no mismatches are found. The algorithm correctly returns mismatched_count equals 0 without any extra handling required for this scenario. This solution implements the function heightChecker to solve the LeetCode problem number 1051, heightChecker. The function takes an input list heights, which represents the heights of students standing in a line. The first step is to create a sorted version of the heights list called sorted_heights. Sorting the array allows us to determine the correct order of the students based on their heights. Next, the code iterates over the original heights array and the sorted_heights array simultaneously using the zip function. For each pair of values, original from heights and sorted_value from sorted_heights, it checks if the two values are different. If there is a mismatch, it increments the mismatches counter. The counter mismatches keeps track of the number of students who are not in their correct positions. At the end, the function returns the total count of mismatches as the result. This solution has a time complexity of O(n) log n, due to the sorting step, where n is the length of the heights list. The comparison step has a linear time complexity of O(n), making the overall approach efficient for the problem's constraints. This is the Java implementation of the heightChecker problem from LeetCode. The logic mirrors the given Python implementation, where the input array is sorted and compared with the original array to count mismatches. Key differences include type declarations for arrays and variables, as well as the use of Java's arrays.sort method to sort the array. The solution is encapsulated in a class and follows standard Java conventions. In this problem, we need to determine how many students are out of place when their heights are compared to a sorted version of the same list. For example, given the input heights 1, 1, 4, 2, 1, 3, the first step is to sort these heights in non-decreasing order. The sorted version of this list is 1, 1, 1, 2, 3, 4. Next, we compare each element in the original list with the corresponding element in the sorted list, counting how many positions have mismatched values. Starting with the first two values, 1 matches 1, so there's no mismatch. The same is true for the second pair. However, for the third value, 4 does not match 1, so we increment the mismatch count to 1. Continuing, 2 matches 2, so no increment here. But for the fifth value, 1 does not match 3, so the count increases to 2. Finally, 3 does not match 4, bringing the count to 3 mismatches overall. Therefore, the output for this input is 3. For the next example, the input heights are 5, 1, 2, 3, 4. Again, we start by sorting the list, which results in 1, 2, 3, 4, 5. Now, we compare each element between the original and sorted lists. The first value, 5, does not match 1, so we increment the mismatch count to 1. For the second value, 1 does not match 2, so the count becomes 2. Similarly, 2 does not match 3, increasing the count to 3. Then, 3 does not match 4, pushing the count to 4. Finally, 4 does not match 5, so the mismatch count becomes 5. Since every element is out of place, the total number of mismatches is 5, and the output for this example is 5. In the final example, the input list is 1, 2, 3, 4, 5. Sorting this list results in exactly the same order, 1, 2, 3, 4, 5. Now, when we compare each element, 1 matches 1, 2 matches 2, 3 matches 3, 4 matches 4, and 5 matches 5. Since there are no mismatches between the original and sorted lists, the mismatch count remains 0. This means that all the students are already in the correct positions, so the output in this case is 0. The time complexity of the height checker function is determined by two main operations. First, we have the sorting step. The sorted heights function sorts the input array, and this operation uses Python's timsort algorithm. Since timsort has a time complexity of O and log n, this becomes the most computationally expensive part of the function. Second, there's the comparison step, where we iterate through the heights array and the sorted version of it simultaneously using the zip function. For each pair of elements, we check if they match, and this involves a simple loop that runs in O, n, time. When we combine these two parts, the sorting step dominates, so the overall time complexity is O, n log n. Even though we add O, n, for the comparison, it doesn't change the dominant term, leaving the total time complexity as O, n log n. The space complexity of the height checker function is influenced by three main factors. First, the sorted heights operation creates a new array that holds the sorted version of the input. This additional array takes up O, n, space, where n is the number of elements in the input array. Second, the timsort algorithm itself requires O, n, auxiliary space for temporary buffers during the sorting process. Finally, the function uses a few variables like mismatches, original, and sorted_value, which take up constant space, or O1. When we combine these components, the total space complexity is O, n, for the sorted array, O, n, for the auxiliary space during sorting, and O1, for the additional variables. Adding these together, the overall space complexity simplifies to O, n. When we analyze the best, average, and worst cases, the results are consistent due to the dominance of the sorting step. In the best case, where the heights array is already sorted, the sorting operation still takes O, n log n, time, and the space complexity remains O, n. In the average case, for a randomly shuffled array, the sorting and comparison steps behave the same way, so the time complexity is still O, n log n, and the space complexity is O, n. Even in the worst case, with a reverse sorted array, the time complexity does not change, it remains O, n log n, because timsort's performance is unaffected by input order. For comparison, a brute force approach that checks mismatches through nested comparisons would have a time complexity of O, n squared, which is far less efficient. The current solution is optimal because it combines sorting and a single pass comparison, achieving O, n log n, time complexity. To mathematically prove the big O complexity, let's break it down. The sorting step involves dividing the input array into smaller parts and merging them back together. This process requires log n levels of division, and at each level, the merging operation processes all n elements. This results in a total time complexity of O, n log n, for the sorting step. Next, the comparison step involves iterating over the array once to compare the original and sorted values. This is a linear operation and contributes O, n, to the total time complexity. Since O, n log n, dominates O, n, the overall time complexity is O, n log n. For space complexity, the additional space required comes from the sorted copy of the array, which is O, n, and the auxiliary space used by timsort, which is also O, n. Together, these result in a total space complexity of O, n. When working on the height checker problem, there are a few common mistakes that can lead to incorrect results or inefficiencies. First, not identifying the sorted order of the array is a frequent issue. Some might assume the input is already sorted and skip the step of explicitly sorting it, but without that step, it's impossible to reliably compare positions and find discrepancies. Another mistake is performing incorrect comparisons, such as aligning elements in the original array with the wrong indices in the sorted version. This misalignment can lead to false positives or negatives, giving you an inaccurate count of mismatches. Lastly, relying on inefficient sorting algorithms like bubble sort can significantly slow down your solution, especially for larger inputs. Using optimized sorting methods like merge sort or Python's built-in sorted ensures your solution remains efficient and scalable even for arrays with tens of thousands of elements. Now, another frequent pitfall is overcomplicating the problem by introducing unnecessary data structures such as hash maps or doubly linked lists. While creative, these approaches often make the solution more complex than it needs to be, adding unnecessary overhead in implementation and debugging. Simpler solutions, like directly comparing arrays, are typically sufficient. Ignoring edge cases is another major issue. For instance, you should test scenarios like arrays where all elements are equal, arrays that are already sorted, and arrays with only one element. Overlooking these can cause your solution to fail in real-world usage or during testing. From an interview perspective, this problem is a great opportunity to demonstrate pattern recognition. It's a classic example of comparing an input to its sorted version, and variations often involve analyzing mismatches, inversions, or the minimum swaps required for sorting. Aim for an O(n) log n solution due to the sorting step, while the comparison itself should remain O(n). Always ask about constraints, like the size of the array or value ranges, and make sure to address edge cases and trade-offs in your explanation. For example, if you propose an alternative method, discuss how it balances time complexity and space usage. This problem also shares similarities with several related problems that you might encounter. For example, missing number involves finding the missing value in a sequence, often requiring sorting or summation techniques. Find all duplicates in an array uses mismatches and array indices in a way that's conceptually similar. Another related problem is sort colors, which focuses on efficiently rearranging elements of specific types. And first missing positive involves using sorting and indexing to find the smallest missing positive integer. Additionally, there are alternative approaches you can explore for the height checker problem. The two-pointer technique, for instance, can be faster for certain sorted or nearly sorted inputs, though it may not work universally. Counting sort is an excellent choice when the value range is limited, such as heights within 1 to 100. This method reduces sorting complexity to O(n), but it does require extra space. Custom comparator sorting is another option if the problem involves specific sorting rules, though it can make the implementation more complex. Each of these approaches has its trade-offs, so consider the constraints and requirements of the task when deciding which to use. Great job following along. We've covered the height checker problem, discussed its solution, and highlighted key takeaways. Remember to keep practicing similar problems to strengthen your skills. Thanks for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!